As electricity end users, when we plug something into an outlet, we expect it to turn on. We expect to receive electricity, always and instantaneously. But sometimes delivering electricity is much more expensive than usual. What if we, the end users, were okay with some of our load being shifted to other times in the day away from these high prices? This changing of end user consumption patterns in response to prices is called demand response. What would be the best way to schedule demand response events? This is the question I've been working on with other researchers from the University of Maryland, along with our corporate partner, Whisker Labs. By remotely manipulating thermostat set points on internet-connected devices, we are able to shift air conditioning load from periods of high prices to low prices. Because most of our customers live in Texas, there is a lot of AC load to shift. When electricity prices are stable, we leave people alone. But when they go up, we increase people's set points so that they use less electricity for AC. When the prices go back down, we return their set points to normal. This way, we are able to do demand response with residential customers, something historically common only in commercial and industrial sectors. Knowing how much load can be shifted this way involves modeling house thermodynamics. I use regression equations fit to pseudodata output from a gray box thermodynamic model to calculate the amount of load that can be removed during demand response and the amount of load used to recover a house to its original set point. Once I calculate how much load can be shifted at any given time, I can schedule these demand response events optimally throughout the day using dynamic programming. Dynamic programming creates a roadmap through the tree of possible decisions for the day, choosing the branch that generates the maximum savings per customer. I describe a customer's state at any time of day as how much demand response they've experienced up to time t, and if they're currently in a DR event. At every stage, there exist actions, meaning demand response of different duration, that could be initiated for each customer, and the resulting next state for that customer. Thus, we model each customer's past, present, and future, and can find the optimal schedule to generate the most savings. For example, the dynamic program could find the optimal demand response schedule for a day to be a 1-hour event at 2 p.m. and a 3-hour event at 6 p.m., saving 50 cents per customer. So far, our results have been very promising. The dynamic program is fast enough for real-time decision-making and has shown that we could save as much as $15 annually per customer. This may not sound like much, but reps control tens of thousands of customers, so our methods could save almost $1 million annually. But our results have also shown that events have to be called accurately, or else reps could save less money or even lose money. This is why our future work will focus on further modeling how much risk reps take on when calling demand response using our dynamic program. Finally, I would like to thank my advisor, Dr. Gabriel, and our partners at Whisker Labs.